hello everyone also from my side. My name is Eike Petersen. I'm a postdoc at the Technical University of Denmark, and I have the honor of introducing our next two speakers. And the first of those is Amar Kumar, who is a PhD student at McGill University in Canada. And he will be presenting about debiasing counterfactuals in the presence of spurious correlations, a paper which was presented at our MICCAI workshop. And in fact, it won the Best Oral prize at that workshop. And so we are very happy to have you here again, Amar. Please, the stage is yours.
Perfect. Thank you, Ike. I hope everyone can hear me. Just checking.
Yeah, sounds good.
And is my screen visible as well?
Yes, looks good.
All right, perfect. Thanks. Hello, everyone. And I'm Amar, as introduced. So I'll be presenting this work, which was submitted to FAIMI Workshop at MICCAI, titled as Debiasing Counterfactuals in the Presence of Spurious Correlation. So let's jump right into it. So the motivation behind this work is that deep learning models, although they have proven to be very useful in medical imaging and has been able to attempt a lot of problems, they are still prone to addressing this concern of optimizing for majority population. What that means is, consider a scenario where you have sick patients who contain medical device and you have healthy patients who do not contain medical device. And there can be disease that needs to be interrogated or disease that need to be identified based on these chest X-ray scans. But deep learning model, instead of learning about disease, they try to latch on to this spurious correlation in this context where disease will be equal to medical device. So instead of looking at the disease, these models try to focus on medical device, and based on the presence of medical device, the decision is made that if there is a medical device, the patient should be sick. Or if there is no medical device, the person is healthy. However, that's completely wrong. So essentially what we need is an explainability for this, where we can explain or try to show that the model is right, but for wrong reasons. So essentially what we are trying to do in this work is counterfactual generation to understand the decision made by model. So specifically in this context, if we try to take a look or via counterfactual generation, the real subject is shown on the leftmost side, where medical devices are shown in cyan boxes. And if you try to synthesize a counterfactual image where the counterfactual image is of a healthy patient, and you try to take a difference map between the real patient and the counterfactual, these different maps flares up in the region where medical devices are present, showing that the medical device are the one that are responsible for making these subject sick. And based on our understanding, we know that this isn't true. So essentially, there is a need to debias as well as explain what the model is looking at in order to make its decision. So if we look at the background for some of these works, there has been previous work which is associated with debiasing, mainly the approaches such as sharpness-aware minimization or stochastic weight average density. There has been a large amount of work on explainability as well, which are associated with GradCam, Lime, SHAP, Gift-Explanation, or other recent approaches, which is based on counterfactual explanation. So I'm not going to go to the details of all these works, but if you're interested and want to have a look, you can take a look at this reference. In summary, what we are trying to do is to debias and explain at the same time. So we are proposing an end-to-end framework where we try to debias the dataset as well as explain to ensure that the model, while making the decision, is not latching onto any spurious correlation, rather latching onto the disease pathology. So the approach that we have is to answer these questions, which is explainability via counterfactual images, and we are trying to debias the results that we have. So the core of this work is to answer these questions: that can a model be trained to disregard spurious correlation and identify generalizable predictive disease markers? And this was also some of the questions that was posed in the chat for the keynote session, that how do we generalize a model? And a lot of time these generalization fail when trying to generalize on a smaller subgroup or a smaller population. So let's try to take a look at the data set that we have proposed. So we try to show our results on a synthetic, on a data set, which is RSNA pneumonia detection challenge. And in this case, we introduce a synthetic artifact And the artifact was something like this. So if you look at the sick subjects, which are shown on the left side, and the healthy subjects are shown on the right side. So we tried to curate a data set and ensure that most of the sick subjects who contain the disease have a black dot in the center. And there are some patients, which we call as minority subgroup, who are still sick, but do not contain this black dot. And on the right side, where you have the subgroups for healthy subjects, there are majority of healthy subjects do not contain this black dot. However, there is a minority subgroup of healthy subjects who contain these black dots. So essentially, the diagonal terms of these matrix, they are majority subgroups, which still follows the same relation, which was explained earlier, that most of the sick subjects contain this black dot and most of the healthy subjects do not contain this black dot. However, we also introduced a minority subgroup of subjects where sick subjects do not contain the black dot and healthy subjects contain the black dot. So that's how we curate this data set. And we also try to show our results on the CheckSpurt, which is the popular medical imaging X-ray data. And in that case, we deal with real artifacts, which is the medical devices in these contexts. So an example of how the data set looks like is shown on the right side. So in terms of methodology, what we have is we try to propose an end-to-end training of generative model, which is to debias and explain the decision of the classifier. And we also propose a new evaluation metric, which I'll show or talk about in a minute, that most of the standard metrics do not address the issue that we are trying to address. So we propose this spurious correlation latching score, where we try to evaluate that the synthesized counterfactual image contains this spurious correlation or not. So in terms of the network architecture that we use in order to explain and debias is using a standard cycle GAN, which contains or which tries to separate the distribution of sick and healthy patient as shown in the red squares over here. So those are the distribution of healthy and sick patient. And the way usually a cycle GAN is trained is you have input image sampled from each of these distribution as shown over here. So you have a unhealthy sample and a healthy sample taken at the same time. And then two generators are trained independently of each other, which tries to change the domain of the input image. For example, if the input image is a sick sample, the generator tries to transfer this sick sample to a healthy sample. And then based on the usual GAN approach, a discriminator tries to discriminate between the synthesized counterfactual image, which is supervised by this black box classifier, which sits at the heart of this network. Now, if you take a deeper look at these black box classifier, this black box classifier can either be two different optimization approach, which we try to use. So the standard optimization approach is called ERM, which is empirical risk minimization. And the debiasing approach that we have used here is DRO, which is called distributionally robust optimization. It's already proven in literature and people have worked on that DRO does debias the data set. Here, what we are trying to show is the explainability that DRO achieves in the context of medical imaging. So a black box classifier, which can either be trained on a DRO-based optimization technique or an ERM-based optimization technique to do this task of binary classification. So given this entire data set of majority subgroup and minority subgroup, how well we are able to debias using DRO on these binary tasks of saying whether the subject is sick or healthy. And in order to evaluate these counterfactual images, they are synthesized based on certain constraints. These constraints are identity preservation, classifier consistency, and cycle consistency. What these means is when a counterfactual image is synthesized for an input image, the original identity of the patient should not change, which is also trying to ensure that the network do not copy any healthy subject or a sick subject, depending upon what is the counterfactual image being synthesized. The classifier consistency, it means that it should belong to the correct class. And the last one, which is cycle consistency, tries to ensure that a counterfactual image, when passed through an opposite generator, for example, in this case, if X of sample of sick subject, which is the counterfactual image over here, if that is passed through the generator, which transfers from healthy to sick, in that case, the original image should be generated. Now, in terms of evaluating these counterfactual images, they are difficult because we do not have ground truth to evaluate a counterfactual image, but we use the standard approach used in literature. So the identity preservation is tested through structural similarity index measure and actionability, which is the measuring the L1 distance between the original image and the counterfactual image. We also use the metric, which is counterfactual prediction gain, trying to ensure that the counterfactual image belongs to the correct target class. However, all these measures do not address this concern that whether the spurious correlation is being addressed or not. Hence, we propose this new metric, which we call as spurious correlation latching score, which identifies whether there is a spurious correlation in the image or not. So if you look at the result, we test the performance of the classifier as well as counterfactual images, both qualitatively and quantitatively. So over here is the classifier evaluation of the two optimization approaches that we suggested in the paper. So the purple one is ERM, and dataset 1 is where we have the synthetic artifact, and dataset 2 is where we have the artifact, which is medical images. And if you look over here on the majority subgroup, which is the first and the last, there is very little compromise on the performance. However, there is significant boost in the performance over minority subgroup in case where we have synthetic artifacts. Similar is the case where we have medical artifacts, and we do not see such high of a boost, mainly because these spurious correlation in the medical devices case, these medical devices are of different shapes, sizes, and their location vary as well. So in general, what we conclude over here is DRO performs better, indicating generalization on the underrepresented class, which is the minority class over here. Now, that's not the complete aim, because we also want to evaluate whether this DRO focused on the right region or not. So over here is a qualitative evaluation of the image. So if we take a look at the first row over here, where we have a real image of a sick patient, which contains the artifact, the pathology of the disease is shown in magenta squares, and the artifact is shown in cyan square. So if you look at the counterfactual image, the second image, which is titled as CFERM, in that case, the only difference happens in the region where there is a black dot. So essentially, what we conclude from this is an optimization, ERM-based optimization method focused on these black dot and said or concluded that this black dot is the one that is responsible for making the patient sick, which is a wrong conclusion. And if you look at the counterfactual image, which is synthesized from a DRO-based approach, we see that the black dot in the center is preserved. So there is no latching onto the spurious correlation. Rather, disease pathology is being focused. So in this case, the disease is pneumonia, and where lungs get filled with water. So if you see the intensity of the region of lung, the lung becomes darker, which means that the water content is being removed. And indeed, the network is focusing on the right thing. Similar is the case where the original image is of a healthy subject, and in case of trying to make this patient sick, the black dot is enlarged, which again signifies or shows that this black dot is what is responsible for making this person healthy. But again, that's not the case, and indeed is associated with the lungs. So those are some of the qualitative results. If you want to take a detailed look, please take a look at the paper. And the conclusion from this is that significant changes in the artifact is shown by ERM. So ERM focuses on the spurious correlation, and DRO focuses on the disease pathology. In terms of the quantitative result based on the scores that were explained earlier. So if you look at the standard score, which is actionability, SSIM, and counterfactual prediction gain, there is not much difference between ERM and DRO, which shows our point that they do not address the concern that we want to take a look at. However, if we take a look at the score that was proposed by us, SCLS, and lower SCLS score is better. If we take a look at the ERM, the score is 0.80, which is way higher compared to the score received from DRO, which is 0.12. Similar for the dataset 2, which is the actual medical devices, spurious correlation. In that case as well, we see a lower SCLS score for a DRO-based optimization network. So from this, we evidently conclude that DRO-based classifier do not latch onto the spurious correlation. But if you want to address the concern that whether it latches onto the disease pathology, that requires more validation, where we want to have ideally a ground truth for disease pathology. So in conclusion, what we have is safe deployment of deep learning models in medical imaging definitely requires explainability in the context to expose and mitigate spurious correlation or biases that are present in the dataset. As a contribution to this work, we proposed the first end-to-end training strategy for generating unbiased counterfactual images, where we debias the data and show that DRO-based classifier can be used to enhance generalizability. But this is only one kind of bias that we have addressed, and we are working on some of the future works in this direction to show that some of these methods can indeed be generalized. So as a last slide, I would like to thank you all for inviting me to this talk, as well as thanks to all the audience for patiently listening to me. We would also like to thank our sponsors who have generously contributed to support this work, which is shown over here. And I'll be happy to take questions if there are any.
Thank you, Amar. That was a great talk. I'm personally also super interested in the whole spurious correlation thing. We don't have any questions right now, and we are also running a little short on time, but I will maybe ask one question. So the examples that you showed, they were all with very localized artifacts, right? So both your synthetic artifacts as well as the medical devices in the chest X-ray case. Do you have any idea how to translate this kind of method to non-localized artifacts?
Yeah, so that's what I'm currently working on. So trying to generalize a method, and we are exploring a bunch of debiasing methods because, as I said, there are many, and also depending upon in the context of bias, like what kind of bias and what are the sources of bias in the image. We are trying to perform some adversarial training in order to see that can we learn or can we generalize this, what are the biases that are present which are non-localized, and once we identify them, can we also try to address and remove those bias and then try to retrain the network so that the performance is improved. But that as well, it's a very tough task, especially in the context when you don't know what these biases are. Some of them may be visual, some of them may be because of features like age or gender or demography. So it's an interesting entangled problem between the visual artifact that we see as well as these tabular information or clinical information that are being present. But but we are working on addressing this right now, which can translate to the clinical context.
Super interesting. I'm very much looking forward to that. So thanks again.